Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. Hey everyone, so today this session will be a code along session of implementing Unet with TensorFlow and Keras on Brain-MRI segmentation. And the dataset is a pretty popular one in Kaggle called Brain-MRI segmentation. And the overall total size is 1.06 GB, so it's not too large. And let's quickly take a look at the dataset. So this dataset contains brain MR images together with manual FLAIR abnormality segmentation mask. The image were obtained from the Cancer Imaging Archive. They correspond to 110 patients included in the Cancer Genome Atlas. Lower grade glioma collection with at least fluid attenuated inversion recovery, which is a full form of the word FLAIR sequence, and genomic cluster data available. Tumor genomic clusters and patient data is provided in data.csv. So that was some technical details on the data. And if we look at the data, so this is the way this data tree is structured. So this folder at the top that represent one single patient, and each folder consists of around 20 TIF images .tif. So if I just go inside the folder, so these are the individual images inside it, and they're all TIF. And for each TIF, I also have a corresponding mask image, and like this one. And the mask image ends with this particular string _mask. And we will be using these in a second to segregate these images. And also in terms of the naming convention for all these images, so the first part, this one, TCGACS, these represent the institution from where it came. Actually, this is TCGA, this part. And then this next part, that represent the patient ID. And finally, this is a slice number of that particular patient. So this is how the naming convention here has been applied. All right, now let's going back to the VS Code, because now my entire code implementation. First, importing all the libraries. Size actually loading a image path and mask path paths. Note that for each of the TIF magnetic resonance image, there is a corresponding mask image. So what I'll be doing is I'll be defining two lists, one containing all the TIF MR images and the other for all the mask images. Containing the word mask. blob, and I have already downloaded the dataset in my local machine, and that's actually kept at it should pick it up, but it's picking up anyway. I say segmentation. 3M. Then let's quickly take a look at that. Kaggle 3M. Then I have one folder, and then inside each folder I have all the images. All right. I will give 1 star here, and then mask. Okay, so this will go Kaggle 3M, another subdirectory, and then finally this will contain the image. That is because here I'm picking up all the mask files. That's why I'm mentioning asterisk mask. And now the list of all train files, that is all the image file, will just be the same list, but all the files which will not have this mask part in their name. For I files, file name. All right. I think my tab and enter is not taking. All right. Image file name string.image, and that will be my I dot replace or mask with nothing, empty string. All right, let's quickly print my image file name, the first 10 maybe. Not print. Let me check. Yeah, so I was missing an asterisk after this, because otherwise it will not pick up the extension part of the file names. All right, now let's run it. Yep. So these image file names will contain a list of all the individual file names. Yep, so I have 3929 number of total images. All right, now let's plot some images and mask. Actually create a separate file called utils.py for all my utility functions. the figure. The first one is fixed. That will be okay. I import all these. Well, otherwise I will. Be looping over a range of starting from 1 because I'm building a grid here. So the total number of images will be, or the total number of cells in the grid will be kind of rows into columns times columns. Because range does not include the last one, I have to add a plus here. Right, here, add subplot. Rows and rows, columns, and the current index. Least I'm taking the current index from that. Now I need to read the image with CV. I imported CV2. Ports. I am read h1 m. I need to convert the color from PGR to RGB, so let's do that. Color. PGR to R. Okay, see. B to RG. Mask will be similarly CV2 dot IMRead. LT.image. Okay. And here put alpha equal 0.4. I need to import all methods from utils from import star, and now get that, execute that method dot h1. I need to pass a 3x3 grid, so 3, 3, then will be image file names, file name string mask files. And run this cell. Awesome. So these are the images from the dataset. It has randomly printed some actual image and some mask. So I think this should be the mask one. And now I'm going to create a data frame from my train set, validation set, and test set. Data will be image file trains. Sorry. Train. And that will be image file and string. And my mask will be mask files. Mask files. And then apply train test split on this data frame. Yeah, actually, test size will be 0.1. Only 10% I'm keeping for test size. And again, further split this to validation set and validation and trend. So what I'll be doing is trend test split. To that I'll be passing df trend and test size will be 0.2. That will return me df trend and df val. All right, let's quickly print some of these shapes. df trend. Oops, sorry. df trend.p. Val and all right, so I have got this division between them actually. Anyway, leave it. All right, now I will be using data generator. That means I will be preparing my data set to pass batch by batch data to my model. For that, I need a data generator and also data augmentation. So for these data generator part, I'll be using a particular rather very standard boilerplate code from a popular repository. So let's go to that repo. And here is that repository. So I'm looking at these Unet. It has got a 3.9k stars, and I will be very much using their this function. So this is a very standard and very popular code implementing Unet. So that's why I'm going to use the same in my code. So let's first keep a reference of that code here. Sorry, that will be this. All right, and I can actually copy paste the entire thing from there. So let's copy this entire thing up to return. Where is my return? So this is generating the train image generator part, mask generator part, and then I have train generator, and the final final return from here for image mask in train generator. So finally they are just yielding these image and mask for batches. And remember, note that here I'm using he's using yield instead of return, because these values will be for each batch numbers, and that's why this is rather perfect. All right, now let's just copy this entire thing, and I'm going to go here and paste the code in my notebook. All right, so basically this function can generate image and mask at the same time using the same seed for image data gen and mask data gen to ensure the transformation for image and mask is the same. If you want to visualize the result of generator, set safe to dir your path. All right, normalize and diagnose. Didn't I define this? Let's define this function. So this will be required because after mask normalization, if the value is less than 0.5 or equal to 0.5, then that mask will be considered a complete black one and does not have any tumor in that. Let's put that actually in comment. So let's do this. This method will take image and a mask. First, let's normalize image equal to image by 255 and mask equal to mask by 255, and then my condition mask needs to be greater than 0.5. In that case, it is a tumor, so classify it as 1. And if mask less equal to 0.5, then it is not a tumor, so classify it as 0. And from this function return image and mask. So in here, mainly what I'm making use of these flow from data frame module. So this flow from data frame takes all these parameters, class mode, color mode, target size, etc. So quickly go through them, what they mean. For example, these one, a class mode. So this will take a binary categorical input, multi-output, raw, sparse, or none. Any of these values as its acceptable values. And default is categorical, and mode for yielding, and this actually controls the mode for yielding the targets, and I'm giving here none. That means no targets are returned. So the generator will only yield batches of image data, which is useful in model.predict. And then the color mode, this one, it can take one of grayscale, RGB, RGBA, default is RGB, and it controls whether the image will be converted to have 1 or 3 color channels. Target size, this one takes tuple of integers representing height and width. The default value is, I guess, 256 by 256, and it actually says the dimension to which all images found will be resized. And save prefix and save to directory are kind of obvious. They take string, and they mainly help you control the way it will be saved. All right, now I have to do a couple of utility function to calculate the metric. For example, the first one would be dice loss. So simply put, dice coefficient is 2 into the area of overlap divided by the total number of pixels in both images. So it's mathematically the expression is 2 multiplied by x intersection y, a whole divided by x plus y. Let's just code it up. Dice coefficients, and it will take y true and y red. I have to flatten it. Y true flatten equal to k dot flatten y true, then y red flatten equal to k dot flatten y red. And then my k is undefined. All right, I have to bring it from here. I think k is comes from keras.background. So this one, TensorFlow.keras import backend as k. And then intersection will be k dot sum y true flatten and y red flat. Oops, sorry, y red flatten. And union will be equal to actually k dot sum y true flatten plus k dot sum y red flatten, and then I will be returning return 2 into union, intersection. Then I also need to add a smooth factor here. SMOOTH. I'm going to define the smooth factor in a second, but let's just put it in the argument SMOOTH. Smooth factor. All right, return 2 into intersection plus smooth, and then the union. That will be union plus smooth. All right. And now dice coefficient loss. It will be just the negative of my dice coefficient. And the next one is the very popular intersection over union. Intersection will be just the usual k dot sum, then the multiplication between y true and y red. So here we multiply, since multiplication will yield 1 only if both the predictions and the ground truth have 1. Otherwise it will be 0. That's the reason intersection intersection actually is trying to find out the common area between these two set, and the sum would be sum y true plus y pred, and IOU is equal to the intersection plus smooth. I need to bring in the smooth factor anyway here again, so SM sum, then minus intersection plus smooth. Then just return this IOU. And just like the previous dice coefficient loss, I need to calculate the loss equivalent here, which is called Jacquard distance actually. By the way, this IOU is actually called Jacquard IOU as well. So what I'm now going to calculate is Jacquard distance. I don't need smooth here. All right, and this will first, let's flatten the flatten would be y k dot flatten y true. Similarly, y pred flatten would be k dot flatten, and then return value will be just a negative of my previously calculated IOU. That will take y true and y predict. So this is I'm just calculating the kind of loss metric for, oh sorry, this will be y true predict flatten and y pred flatten. So this is a kind of a loss metric for my IOU, and just like previously I'm calculating the negative, because if you think intuitively that why we are taking the negative for calculating the loss is because, now first note that, for example, in dice coefficient, when dice coefficient high, that means high accuracy in the prediction. So loss will need to be some quantity that will be high when the accuracy is low, and that's why we take the opposite of the accuracy, and that's why we take the negative of the accuracy number. And later in Unet implementation in this video, when I will be using this loss to be passed into my Adam optimizer, then I have to pass this dice coefficient loss as a loss metric, something like a line like this. So here I'm passing as a loss to my optimizer, to my model that compile this dice coefficient loss, and this will be minimized by the training. And minimization means I have to continuously reduce it through the training, and that means I'll be actually maximizing my accuracy. So when I'm minimizing my negative term of the dice coefficient loss, I'm actually maximizing the dice coefficient, which is good, which means more accuracy. All right, so now I'm done with Jacquard distance, and now I think I'm ready to implement the Unet. So now I start building the Unet architecture. Create a new file, and here there will be my whole Unet architecture. And just before doing the architecture, let's quickly have a look at this the overall architecture. 1 second. So this is my regular unit architecture. It starts with these. Let me zoom out. So here, the first leg here, it's the encoder part or the downsampling part with feature extraction, whereas this is the decoder leg or the upsampling part. So feature maps from the encoder are concatenated at the decoder through the skip connection, and these gray lines represent those skip connection and the concatenation line. So with this skip connection, at every step of the decoder, we use these skip connection by concatenating the output of the transposed convolution layers with the feature maps from the encoder at the same level. So it will be something like this. Let me zoom in a little bit. Sorry. So at the level U6, that will be concatenation of U6 plus C4. Then at the level U7 will be a concatenation of U7 plus C3 and so on. U8 equal to U8 plus C2 and U9 plus C1 will be U9. So because that's how it is concatenated. So this is kind of my U6, and I'm concatenating C4 with that to get my output at this layer. So from these image of Unet, let's take a look at the very first operation here, that is just in this section of the image. Notice that each process constitutes two convolutions layer, and the number of channel changes from 1 to 64. As convolution process will increase the depth of the image, and this red arrow pointing down is the max pooling process, which will halve the size of the image. And also these changes from 572 by 572 to 568 by 568 is due to the padding issues, but normally the implementation of Unet uses padding equal to same. And so the same operation is kind of repeated 3 more times, 1, 2 and 3 in these 3 sections. And then from here starts second leg, that is the deconvolution part, and this is also called the decoding path or the expansive path. And in this expansive path, the image is going to be upsized to its original size by the end here. That is after going through many up convolutions layer, and because they are up convolutions, in this leg we'll have to use transposed convolution. All right, so with that, now let's get back to our unet.py file and let's start implementing this. So I will have 1 second. Include size equal to, I'll give it 256 by 256 by 3 channels. Inputs equal to input size. Why it's saying undefined? Oh, obviously because I have not imported this thing. So let's just import everything from, I guess, here. For now, I'm just going to import every module. Later, I will fine tune the non-used ones. Not here, here. All right, now it should be okay. Input size. So first is our encoding leg. Filters equal to 64. So this conv, again, why I'm getting conv to be is not defined. Didn't I import it? Sorry, that's a spelling mistake. All right, so filters is the first parameter or the first argument to conv2d, and this actually is an integer which represents a dimensionality of the output space, that is a number of output filters in the convolution. And the filters argument sets a number of convolutional filters in that layer. And another way to put it is that filters are the number of features you want to detect in the image, and it is a hyperparameter. That means it is entirely up to you how you want to set it. So I'm setting it at 64, just following the original Unet architecture that we just saw. Kernel size would be 3 by 3, and padding is same. With that, I have to pass inputs. Then batch normalization, that would be activation. Value to that I will pass conv1. Then my conv1 now becomes modified. That will be the second conv2d. And filters remain 64. Kernel size remains 3 by 3, and padding equal to same. That I pass bn1. Then our next batch normalization, activation relu conv1, yeah, makes sense, and also bn1 equal to activation relu bn1. Okay, then max pooling. So I'll be defining a max pool layer, max pool 2D layer. Pool size will be equal to 2 by 2, and to that I have to pass bn1. All right, so now that's one block of convolution, and now I just have to repeat it. So let's copy and paste and change some of the things. So this will become conv2. Filter size now will become 128. Kernel size remains same. Padding same. Inputs. Activation will become conv2. All right, this will become conv2. Filters 1 to 8. Kernel size 3 by 3. Padding bn2. Oh, I have to, yes, bn2 conv2. Yep. Now bn2 will become my conv2, and bn2. All right. And this pool will become pool 2, and that will be my bn2. Oh, here it's the last output layer, which is pool 1. All right, let's repeat this again. And this will become conv3, conv2d, and now my filters will be 256. Kernel size remains same, padding same, pool 2. Make the similar changes for the next lines. Conv3, conv3, conv2d, filters 128, and bn3. bn3 becomes conv3. bn3 becomes my bn3. And this is pool 3 and pool size 2 by 2 bn3. All right, makes sense. Similarly, I'll have the next two blocks like this, and then I also need a conf5 block. Let's do it. Conf5 equal to conf2d. Filters will be 1024 because we are doubling the filter size here. So our previous was 128, 256, 256, then 512, and then 1024. Kernel size 3, 3. Padding SAM. All right, and to that I will pass pool 4. bn5 would be equal to activation value conv5. Conv5 equal to that will be conv2d. Filters kernel size padding is same. To that I pass b and 5. And now I need to use a batch normalization along the axis of 3 and conv5. bn5 would be activation value bn5. All right, here ends my encoding leg of the Unet, and then I need to start the up convolution. That is the up convolution of the decoder leg, which will use conf transpose 2d. Let's put a quick documentation note here. Yeah, so the gray arrows, these gray arrows is referring to these image that we saw over, where was that? One second, here. These gray arrows in my up convolution leg will be concatenation. We will see that in a second. So those gray arrows are actually skip connection that concatenate the encoder feature map with the decoder, which helps a backward flow of gradients for improved training. So my first one will become conv6. So I'm just referring to another note here that we previously said. So U6, that is here, it will be a concatenation of U6 plus C4. That's what you're going to implement here. Conv6 should become concatenation. Concatenate, and between, because now I'll be using conf transpose 2d, conf 2d transpose. To that I'll pass 512, kernel size 3 by 3, paddings, no, kernel size here will be 2 by 2 actually, and I also need a stride that would be equal to 2, 2 as well. Padding SAM, and to this padding SAM and here I need to pass the previous layer, which is bn5 comma conv4. All right, so my conv4 is this one, which I'm concatenating with these conv transpose 2D, and that concatenation result will be my conv6. So going back to the image here, so this is where I'm taking the 512, and this is getting concatenated with these C4, that is conv4 in our case, conv4. And all right, so there will be my square bracket, sorry, where is that? Square bracket is already ending here, and I also need to mention the axis along 3. All right, then bn6 is equal to the deviation value. To that I'll pass conv6. Now conv6 equal to conv2d. That will be filters equal to 512. Kernel size. Why I'm not getting the intelligence? Doesn't give me 3x3. All right, just type kernel size would be 3, and my padding here as well will become same, padding same, and bn6. All right, now again bn6 equal to batch normalization along the axis of 3, and to that I'll be conv6 bn6 activation relu conv6. No, that will be bn6. All right, now same way I need 2 and actually 3 more blocks like this, which will be my so this is my number 6. I need 7, 8 and 9. So that would be this up 7 concatenate. Let's quickly check if I'm doing it right. Up 7 concatenate conv2d transpose 256 kernel size 2x2 stride padding. To that I pass bn6. This I am concatenating with conv3, and that concatenation result is my up 7. So yeah, so up 7 means u7 plus c3. All right, similarly so then my regular conv2d activation, conv2d batch normalization activation, and up 8 will be concatenate conv transpose 2d. To that I have to concatenate conv2. Again, going back to our yeah, u8 plus c2 becomes my up 8. All right, and along the axis 3, and the other layers remains just equivalent conv2d activation, conv2d batch normalization activation, and up 9 is these conv2d transpose and conv1, that is u9 equal to u9 plus u1. Yep, along the axis of 3, and the rest remains equivalent code. All right, now I can actually come out of these blocks and do my last layer, which is conv10. That will be conv2d filters will be 1. This is the last layer. Kernel size will be 1 by 1. Activation sigmoid. To that I pass dn9. And this is what I return. Model dot model, and that would be my inputs would be equal to inputs actually, and output equal to conf10. That is last result. All right, that completes my Unet. So now back to my notebook, and I need to import the new files for Unet. All right, and now I should be ready to start the training. But before starting the training, let's define few things like training parameters. As a train generator, yes, rotation range equal to 0.2. Let's do, with shift range. Shift range should be 0.05. Height shift range I'm also keeping at 0.05. Shear range, that keeping at 0.05 as well. Zoom range, yep, 0.5. Horizontal flip would be set to true. The mode is nearest. All right, that should do. Now train generator. To that I pass df train. Did I define batch size? I don't think so. Let's define few hyperparameters, which are epoch would be, keep it at 100. Batch size, have I defined it earlier? Quickly check. No, batch size is 32. Learning rate 1e minus 4. Train generator df train, and then next will be batch size. Train generator param. Target size is the tuple, which is image height and image weight. Why I'm getting, let me see. So there was a spelling mistake here, I just corrected. And before the training, I also need to do the same line for my test gen. Equal to train generator df test batch size, and because it's a train set, I only need to define a dict like this as my third argument, which should have been the train generator param. That is all the augmentation param, but because this is my test set, so I'm not going to separately apply the augmentation. All this augmentation will only be applied on the train set. All right. And so what else? I need to give target size here. All right. Right. And now my model. Okay, before that, remember this train generator is something that we defined a little while back, and that is this function that we referred to our very popular Unet repository in GitHub, this one. So we have taken this train generator method from there. And all the augmentation, that is the third argument to my train generator method, and that will actually be invoked to the image generator module right here when all the augmentation on the images will be applied. Anyway, moving ahead, model. That will be my Unet. Input size will be equal to IM height, IM width, and also the channel, which is 3. Then let's define a decay rate for my learning rate. The learning rate divided by EPOCH. That's how the learning rate will continue to decay. Now, optimizer. I'm going to use Atom learning rate equal, LR equal to learning rate. Beta 1 would be 0.9. Beta 2 I'll give 999, 0.999. Epsilon I want to keep none, and decay will be decay rate. What else? I need to also give AMS grad, which I'm setting to false. All right, so that's my optimizer. And now model.compile. Optimizer equal to optimizer. I need to give the loss because it's a segmentation problem, and we have already defined the dice coefficient loss. So that's what I'm going to do here. Dice coefficient. Sorry, what was the name? Let's go back to our utils file. Yeah, dice coefficient loss. Was this? Yeah. Dice coefficient loss. Matrix should be. This is going to be a binary problem. So yep, let's give it binary accuracy. And then IOU and dice coefficient. Oops. Pressing enter takes me to the next line. COEFF. What was that? Yep. It says it's undefined. Let me check. And while I am in this file, just noticed a small mistake here that I used yTrue twice, so it will be ypred. That was a small mistake. So there will just be another S here, dice coefficients. All right. So these matrix argument. This actually is a list of metrics to be evaluated by the model during training and testing, and the matrix argument should be a list. Your model can have any number of metrics. All right. Now I need to define a callback. Callbacks could be fine. Model checkpoint. Oops, model checkpoint. That I would name it as Unet underscore Unet dot HD. F5. Verbose equal to 1. Save best only equal to true. All right, now history would be model the fit to that I'll pass train underscore gen. What else? Steps per epoch. Step per epoch will be that would be the batch size. So len df train divided by batch size. Oops. BA batch size. So this is actually the number of samples in a batch, and then epochs equal to HS. Also, I need a callback. Callbacks equal to callbacks. Validation data will be my test underscore gen, because that's my validation data. And validation steps should be len of test df test divided by batch size. All right. Now, okay. So with that, I can actually run the training. Yep. And when I executed this last cell, that is a training cell, I got a couple of error. All right, this one, unexpected keyword argument passed to optimizer, decay railed allowed keywords are global CLI norm, decay CLI norm. Okay, so I got it. So I have used the wrong keyword argument. Here it would be just decay. Let's run it again. All right, unsupported operand type for /int. Yes, here. So let me fix that. So this is coming from where I defined my batch size, and that's here. There is an extra comma here. So run from here again. Again, missing one required positional argument, smooth. Right, I need to give this smooth argument. Let's define the smooth as a hyperparameter to be 100. So whenever I'm using my dice coefficient function, that requires this argument here. So this requires smooth, and also IOU requires smooth. All right, so let's see where I'm using dice coefficients. Right here. Actually, this function, this is just a this model.compile. This takes dice coefficient as a function as one of the metrics. So where I'm executing dice coefficient is actually here while calculating the loss, and that would take smooth parameter SMOOTH, and here as well is SMOOTH. All right, let's define the smooth actually to be, give it a value of 100. Okay, that's the default value, and that means I need to re-import this file again. So I'm executing this imports cell again, and then run from, yep, this cell. I'm still missing one smooth argument. Okay, let's find out. All right, I just figured out a small but very nasty bug I had in my code, which is in my dice coefficient. When I was calculating the intersection between two sets here in this line, I did not multiply these two tensor. Rather, I used I used this comma here. So it would be a star, that is multiplication of y true flatten and y pred flatten. Okay. So now finally my training is going on properly. Let's run through 100 epochs and see the result. I'll show you the output at the end. So after running for 150 epochs, this is the kind of loss I was getting. So let's check out. At epoch 150 of 150, I got a loss of 0.9280, binary accuracy 0.9986, IOU as these, and dice coefficient of 9279, which is pretty good dice coefficient indeed. And now I have to plot the result. So I need to grab all the parameters from the history object that is left over after the training. So let's define a variable history post training equal to history dot history. I'm just going to take the list of all the dice coefficients. So let's train dice COEFR would be equal to history dot, history post training dot DICE dice COEF. Was this my variable name? I think no. Let's check out. So this is my variable name, so I need to pass it accordingly. All right, so that's my list of dice coefficient there. Let's just quick fix something. History post training dice coefficient. All right. Now I also need list of my train history post training, and that would be again, well, what was for the training. Actually, before accessing the history object's keys for plotting them, let's quickly check what are the key values there are inside the history object. So I am inside a Kaggle kernel because this dataset is in Kaggle. And also remember that these history object callback, this history callback is automatically applied to every Keras model, and it gets returned by the fit method of the models. So I'm going to pretty print the dict that the history is. So first importing pprint, it will just pretty print the object properly, and then p.p ry and run this cell. Where did I make the mistake? Module pprint has yeah, of course, pprint dot, it will be pprint, then run it again. All right, so this is the whole history object, and we can see we have this key binary accuracy dice coefficient because that's a method we supplied while compiling the model to the optimizer. I have IOU loss, val binary accuracy, val dice coefficient, and val IOU val loss. All right, now I can access all these one by one for plotting my training progress. So I'm back in my VS Code, and we already earlier defined this history post training object to be history.history, and then I'm accessing the various values from the history keys. So this will be val dice. Then I have now for plotting the accuracy, I need the Jacquard distance, which is IOU in this case. Brain history post training, and that would be IOU. And we do have this IOU in the keys, yes. So I have IOU, loss, val, binary accuracy, val, dice coefficient. Okay. And this dice coefficient. Okay. I don't have any S here. All right. Brain Jacquard list, and I also need a test Jacquard list, and that would be my val IOU, validation IOU. And now I need the loss. For plotting the loss, I need brain loss list equal to history post training, and I need the loss. And also for the validation set, test loss. 1 second. It would be loss equal to history, and this will be my val loss. Do I have val loss? Yes, I have val loss. Okay, and now for the plotting. So first, plt.py. I'll be plotting two plots. So the first plot will be about loss graph and the iteration. That is epochs against loss. So plt.pl plot test. What is that? Test loss list. No, I'll be plotting test dice coefficient. No, actually test loss list, and then p dash p dot plop train loss list. Where is my train loss list? And here as well r dash. Next label would be iterations. This actually is they are the epochs X label, and then plt.y label. That would be my loss. Title. Let's put it loss graph, and font size equal to 12. And now I also need the second plot for the accuracy graph. So plot.value. And actually I can just copy this thing and then change it. So plt.plot, here I'm putting, instead of that, I'm doing brain dice coef, and here I'm doing test dice coef B and R. Okay. Yep. Yeah. And then for the text X label, I have oh yeah, X label remains same, and only the Y label will change to accuracy. And this is accuracy graph. And finally, just plt.show. And finally, when I plot them, this is the plot that I get for plot number 1. It's iteration against loss, and we can see it continues to reduce. And for the accuracy also, accuracy on the y-axis and iteration across the x-axis, and we can see it's reducing. And now finally, I am going to apply the trained model on the test dataset. So first, I need to load the previously trained model. So we previously saved the model in this line here. That is model checkpoints unet.hdf5 saved based only. So I need to load the same hdf5 file here, which is my trained model. So yeah, model equal to load model. Load model in this case net.hdf5, yeah. And I also need to pass all the custom objects, custom objects. That would be my the dict. It will be a dict, and this will have dice coefficient loss, which will be equal to dice coefficient loss. Why it's saying not defined? Let me check. Actually, the original function where I defined the dice coefficient loss, I named it with an S. It should have been without the S, but anyway, for now, let's carry on. And I also need IOU. That would be my IOU, and the last one is my dice coef. Dice coefficient. That's the method that we define. Dice. Sorry, that's not it. Dice. COE. Yeah, this one. All right. And now I also need to do the test. I need to get all my test data set from my generator method. So test gen, and remember we defined the generator method to be train generator. It will generate all the data with image data generator module and pass this data batch by batch to the model. So train generator, and that would be df test, and batch size. Also need to pass all the third argument as a dict format, this third argument had all the data augmentation, but it's a test data, so I'm not doing the augmentation again on the test data, but I have to pass this third argument as just as a dict. And target size, that would be equal to my image size. I am height, and I am width. Results should be equal to model.evaluate. That I pass test gen, and my steps will be equal to len of df test divided by batch size. Now I just want to print my test loss, which will be results ULTS results 0, and also I need to print test IOU. That would be my results 1, and I need to pass the test dice coefficient. So this is the first one is 0 is a loss, then IOU is index 1, and last one is dice coefficient, which is index 2. print test dice COE. That would be my results too. All right, that should do. And with that, when I executed this cell, this is output that I got. So my dice coefficient is 0.8922. Test loss, actually, yeah, test loss is minus 0.8919, and test IOU is 0.99, and test dice coefficient is 0.807. And now the final step, which is plotting the predicted mask from the test image set, because now I already have the trained model, and I'm just going to apply that model to get my prediction from the test dataset. So let's do that. And I'm going to just randomly select around 20 images for this plotting. So I in range 20, index will be randomly selected, so np.random.randint 1 len bf test.index. Thereby I'm randomly selecting one index from the df test.index column, and my image will be just cv2.imread and pf test, then image file name brain dot iloc index. And if you have forgot what is this image file name strain column is, so let's go back to our original code here. So this image file name strain column will hold all the whole path of each of the train images. That is all the images which does not have this underscore mask in its file name. That means they are all the original image which are not the mask, and that's what we want here. So let's proceed. So that's my original image, and I need to resize this image because all my images should be in the 256 by 256 frame. cv2.reshape resize, and to that I'll pass IM height and IM width. All right, and I also need to normalize. And now if I do, this is a three-dimensional tensor, each of this image, and if I print this, if I do something like this, print img.shp, I will get a 256 by 256 by 3 shape. But I need to add another dimension because I need a 4-dimensional array. So what I'm going to do is image equal to, I'm going to use np.newAxis. np.newAxis. To that I will just pass the existing dimension, that is colon, comma, colon, comma, colon. This will take all the existing dimension, and only the first dimension will be the new dimension. And I found a very good Stack Overflow post here. If you're interested, how does numpy.newAxis work and when to use it. So basically this is just to increase the dimension of the existing array by one more dimension. when used once. Thus 1D array will become 2D array, 3D array will become 4D array, and so on with np.newxc. So what I'm doing is here is this one, that is a then slice, and then sorry, I am doing here this one, a np newxis then comma slice. That means it will just add these another extra square bracket, making it by adding another dimension to my original array. All right, so I have, so now if I print this new image, let's comment out because I'm not going to actually print it yet. So image dot shape here, shape, this will give me 1 by 256 by 256 by 3. It's a 4-dimensional array now. Okay, now I have my original image, and now I need to get the predicted image from this original image because I already have the trained model. So all I have to do is model dot predict. To that I have to pass this image. That's all. Let's hold this in a variable predicted img. Yeah. Next, the plotting, plt.ifigure, fixed size will be, let's keep it at 12 by 12 grid, and I'm going to make use of subplot because I'm going to plot side by side original image, original mask, and then the predicted image. So first, in a single row, each of my single row will have 3 columns for the 3 images. So I need a subplot of 1 by 3 by 1 by 3. That is one row, 3 column. Subplot 1 row, 3 column, and then the index. plt.im. Why this? Oh, im show predicted. Not yet. First, let me squeeze this np.sq so that all the extra dimension are taken out. emg. So my first row, first column in each row will be the original image, and then let's give it a title. Yeah, ple image. All right. And then my next image in the subplot, so plt.subplot 1, then I'll be using 3 and now 2. So this will be my predicted, this will be my original mask actually. So because for each original image I need to show the original mask and also the predicted mask. All right, so plt.subplot, then plt.im show. Let's put np dot squeeze this one as well. This will be cv2 dot, I have to read the mask from the mask file names. So cv2 dot im read df cast, and then I need to access the mask column. All right, and then I log index. Okay, so this will catch my mask image. Also, this give a title to this, plt.title mask. And now the final column, which will be my predicted image. So plt.subplot 133, and this will be plt.im show np.squeeze. See, previously I did not need to. This is beautiful. This tab 9, this extension tab 9 in VS Code, it's really working beautifully. The first time I I typed np.squeeze, and the second time I typed np.squeeze, I did not get automatically, these intelligence did not suggest np.squeeze. But after 2 times typing, now tab 9 already knows that I want to type np.squeeze, and it gave me that option. And to np.squeeze, I need to pass the predicted image. What is my predicted image? ing, yeah. And I also need to do a little thing, which is if this predicted image is more than 0.5, because these are probabilities. All right, yeah, makes sense. plp.title TRE-BICTION dot go. And after I executed that cell, I got this kind of output. So the first column is my original image, then original mask, then my predicted mask. So if we go down and see the positioning of the mask, of course, for example, this is a completely dark one. In the original mask, I do not see anything, but in the prediction, I see a little existence of a tumor. So this is kind of not the perfect result that you want, but that's only one example. Otherwise, if you look at most of the examples, the prediction is pretty well predicting the positioning of the mask. For example, let's just take a look at these two shapes. This is the original mask, and it shows the existence of tumor, and the prediction also shows the existence of the tumor in pretty much the same space. For example, this one, original mask is non-existent, means there is no tumor. Prediction also shows no tumor. And similarly, this one, the positioning of the tumor is almost similar between my original mask and prediction. And if I go down, again, good prediction here, very good prediction. Both are predicting no existence of tumor. Again, this one is a pretty similar, in terms of geometry, they are almost same between original mask and prediction. Yeah, so overall looks like the Unet model is working pretty well in predicting the positioning of the segmented mask. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with Pytorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.